find out that, yeah, they're actually pretty good at getting these traits introduced into the population. Right, the reason is that the adult mortality is what's controlling this, because the adult mortality determines how many adults there are to make the larvae. All right, so this is an important part of what goes on in these phase. It's not just the larvae, it's what happens with the adult population, how long they're there, and how long they can continue spawning and producing larvae that eventually do transfer. Because the larvae do transfer the trait, but it's the characteristics of the larvae as well as the adult population that matter. Okay, so last couple of things here. I said at the beginning that the estuaries have a problem with carbonate balance. Okay, shellfish have a shell, right? So in addition to, this is a simplified version of all of that I just showed you. This is the growth and the death of the oyster larvae, the oyster post-settlement population. All right, so this is a simplified form of all the modeling structure I just showed you that goes behind that. This is a shell budget up here. And the way you get shell is that the animal dies, the shell stays on the reef. There is a regular dissolution of carbonate shell by seawater, just burial and that kind of thing. But the addition comes from the dead individuals. All right, so this is a shell budget model in a very simplified form here. All right, so the shells provide a habitat because they give the larvae a place to set. All right, and they're very important for the habitat of the general estuary and coastal waters. All right, so what's shown here is a simulation that says this is the shell mass that you get with this particular mortality rate here. All right, so high mortality here, gives you, it's counterintuitive because the high mortality is giving you less shell. All right, but what happens is that the shell is formed usually by the larger animals when they die. All right, and so if you have a lot of large oysters here with a low mortality rate, you're actually putting in more shell because out here at the higher mortality rates, there are not very many large individuals. All right, now this tells you something about what happens to the large oysters and the shell mass that goes into the estuary as a function of the mortality rate of the large oysters. All right, so out here you're not getting a lot of shell even though there's a high mortality rate. So you want to keep the mortality rates back in here so that the large animals are dying at a rate that maintains themselves, but is also putting a lot of shell into the estuary. But the problem is, this is the fishing mortality. All right, so by fishing the shellfish out here, what it's doing is it's having an effect on the shell that goes into the estuary. All right, and this model is now actually being used to look at shell repletion rates because a lot of states in the U.S. say, well, we'll just buy up shell and dump it in the estuary. All right, well, it's extremely costly to do that, when in fact it might be more cost effective to take this red arrow and shift it back up here. Okay, so in conclusion here, I realize I'm between you and lunch at this point, we have the understanding and the tools to allow us to look at the interactions of ecology, biology, and genetics now. And as I said, this is done in terms of a benthic shellfish or a benthic invertebrate, but the application of the approach applies to pretty much anything. All right, so these models are extendable to other invertebrate species, and I would also maintain all invertebrates. All right, if you have the understanding of the species and you have the data sets, then this provides a framework for looking at this, and it looks at the combined effects of environment, growth, and behavior. And the genetic part allows looking at the projection of effects of climate change, because the genetics is the important part of the adaptation to that. Okay. We can use, I'm not going to advocate, I know we're talking here about Earth system models, and I wouldn't advocate that you take this and put it into one of these Earth system models we've been talking about, but you use these types of complex models to develop the parameterizations that go into the larger models. And I think Barish made the same comment, is that you want to do the know how and what needs to be parameterized to go into the next scale model. And these models are sufficiently robust at this point to give useful inputs for management. As I said, they're used for things like shell repletion experiments, looking at how many animals you need to put in over what time period in order to introduce genetic traits into the populations. And the genetic basis allows consideration for the adaptation part. So I'll stop at that point and ask if there are any questions, and I thank you for your attention. Thank you.
Does the model feed on real data like oxygen and temperature and so on? And so that is causing the wiggles in the seasonal cycle.
Okay. The model, that was the, this, all right, the circulation model there, it gives the environmental temperature and salinity. It also has, which I don't have on here, it has a lower trophic level model in. All right, so it gives a dynamically evolving food field. All right, it could also have oxygen in it. We don't have that, that's not in there now because the applications we're using are in areas where oxygen is not, low oxygen is not an issue. What we're trying to do right now is put pH to look at the effects of changing pH on carbonate ions. All right, so all of that is in there. All right, so we don't have time-varying observations of those fields, but we have enough observations that we can evaluate some of the lower trophic level model that goes into that.
A couple of questions. So there's some assumption made in the feeding. I mean, when you said the size class of the phytoplankton affects the growth rate, they are filter feeders, so you are somehow going directly from phytoplankton and reproduction to growth. Is that efficiency?
Yeah, there's a growth efficiency and all that. Yeah. The interesting thing is that everybody, if you look in the literature, the literature indicates that things like benthic invertebrates, the shellfish and things, are never food limited because there's always plenty of food. But it's not the right quality of food, which I haven't even gone into that. And that's where the shift between the large and the small phytoplankton become important, because the food quality is not what the shellfish need in that particular case.
And when you set these larvae at different ages, do you get like geographic speciation?
Okay, yeah, and in fact, let's see. In this example, this is Delaware Bay, which is on the east coast of the United States. If you look at number 1 up there, it's genetically distinct from 2 and 3. The 2 and 3 are genetically distinct from 4. All right, and that's based upon, again, Schmid-Wood's genetics work, where he's gone out there and looked at those animals. All right, and the distinction is a gradient in resistance to disease. All right, where the ones in the upper bay have no disease resistance at all. Mid-bay is marginal, and the lower bay is where the animals have disease resistance. All right, so the management of these species is to try to take number 4 there, move those animals plus hatchery-grown animals to 2 and 3 to develop resistance there. All right. So, yeah, you can see within a small bay like Delaware Bay, there is genetic distinction among the population.
Your disease pressure depends on salinity?
Disease pressure depends on salinity, and the upper bay is what's called a disease refuge because it's low salinity, and this particular disease does poorly. So one of the other applications here is that in theory, you would never develop disease resistance in the bay because number 1, if you look at the arrows, exports larvae. Right? And as it's exporting larvae that don't have disease resistance. They're going in and diluting the animals that have disease resistance. All right, so, all right, if you were to go at an extreme, you would tell a manager, don't bother putting in disease-resistant oysters because you will never develop disease resistance. But that's not the answer they want. It's one of those, like you're talking about with the human dental image. You know, all we have to do is put them in and they work. Yes?
Presumably, being reef builders, they're rather keen to be in sort of clusters where there's likely to be like a neighbourhood dependency on the characteristics that are there. For instance, the adults are maybe growing strongly, might create micro environments that allow individuals to prosper rather than being so stuck, isolated from the rest of the cluster.
Right.
Is that possible to bring that sort of dependency into a model?
I'm sure it's possible, and this model doesn't have the resolution to allow that, because we have the reef.
So the reef's considered to be literally homogeneous within that sort of environmental spectrum?
But there are people who are working on habitat types of models where they actually look at the physical structure of the reef, and they try to do that. They try to look at the variability in the reef and what that does for the reef building animals, but also the animals or the organisms that depend on the reef for habitat. Right, but this model doesn't have a resolution to do that. Yes.
Do you know what is the reason for this? What is the ecological reason for this reduced connectivity? What is the reason for this bispeciation? Why is there different haplotypes, different types of shellfish? And the meaning of different adaptations.
You mean,
why is it caused? Yeah, what was it caused?
why do the differences in the genetic population occur? Is that, yeah. It's due largely to the salinity gradient in the estuary, and I'm talking here in terms of disease resistance. The salinity gradient, the oyster and the particular pathogen respond differently to low and high salinity. All right, and it's the trade-off between that ends up setting up these different genetically structured populations.
So it can be caused artificially on like pools, can it be caused artificially and then you can remove them to those specific sites?
You don't have to do it artificially. Delaware Bay did a nice natural experiment for us in the 1980s where there was severe drought. And the severe drought allowed high salinity to persist all the way up into the upper reaches of the bay. Right, and what that did is the disease took over the entire bay and pretty much killed something like 80% of all the oysters in the bay. And the people who worked on that were able to look at how the bay repopulated itself. And it turned out that that was the equivalent of the Black Plague in Europe because the animals that repopulated the bay had a different genetic structure in terms of disease resistance. It's easier to let Mother Nature do the experience and no impact statements.
If someone were to try to extend a model like this to a global model, by the form of parameterization, what do you think are the most important variables that would be sort of
well, I would turn that around and say, what is the question the global model is asking? All right, is it carbon export from the bay? As an example, and if that's the case, then all you need is a parameter. All you need to take from this is probably the parameterization for the filtration rate. You know, so it really depends on what it is. All right, if you're asking, can the disease in this bay spread along the east coast of the United States as global warming it expands the potential habitat? All right, that's a different question than what you would want from that is the export from the bay of either the larvae or the pathogen, and some understanding of it. So it really depends on what you're asking.
So this type of genetic modeling is really telling you like how the type of traits you want to put in